So let's make this more concrete because as somebody pointed out, it seemed like a silly computational problem. So we're going to give a classic problem that people solve dynamic programming. I'm going to call it the printing neatly algorithm, and my understanding, I don't know if you've heard of LaTeX. It was designed for math people to write nice papers, and it has to, and evidently I heard that it uses this algorithm. All right, so the input to the problem is a bunch of text that you want to print, and it tells you how many lines are allowed on each character, how many characters are allowed on each line, right? And so here's an example input, right? The text could be sure to be honest and kind, and we want to print it on lines that allow 11 characters per line, right? So what is a solution? A solution tells you how many lines to put on each, how many words to put on each line. So here's a possible solution, right? Be sure to is on one line, be honest is one line, right? All right, so that's what a solution is. And we need to allocate a cost to it. And the cost will somehow indicate how neat it is, how much they all in at the same place. And so what we're going to do is for each line, we're going to count how many blanks there need to be at the end to pad it out to 11 characters. Here I have the periods are indicating blanks so that you can see the blanks. And you might notice I used the font where the width of every character was the same. And so here's the number of blanks on the end. And what we're going to do is we want a small punishment when you have small blanks, and a big punishment when you have lots of blanks on the end. And so the way to punish you a lot is by to cube that number, right? So here, having 3 blanks is really bad. So we'll cube it for a punishment of 27. Everybody understand the problem? And then we add those costs up. And our goal is to break up the text to minimize the sum of the cubes of the number of blanks at the end of each line. Everybody understand this problem?
Yeah.
Excellent. All right. So what's the brute force algorithm? Is you just try every possible way of doing it, and you can see, right? I could say honest and kind, or I could say honest and kind, right? So that's 2 choices and that's 2 choices. And so if the text was just a repeating of these, you can see I have 2 times 2 times 2 times 2 possible paths down this thing, and that's just too many ways to check. Everybody good with that? All right. So we're going to think about, I think, what's the easiest way, the most natural way to approach this problem is to go through the game of life, how you would think about it, right? What you would say, right? You handle the input and the output one at a time, right? You'd say B, oh, okay, let's put B there. We make a decision about each text, where to put it, right? We're just going through life and deciding the objects are coming, and we're deciding for each object. I guess it's a yes/no decision. Do we put it on the same line as we had before, or do we start a new line for it? And sometimes once we finish a line, we can see what our costs were. And everybody kind of get how that's sort of the game of life, right? Going through it. So we want to think, what does Pooh Bear remember as he goes along? Remember, he can't remember all the words that he's done. He can't remember everything that he's all the decisions he made, right? Right. So here's this guy, he knows everything. He has to decide what Pooh Bear really needs to know in order to continue. Anybody have an idea? Does it have to remember how the previous lines were done?
The cost of I like the total penalty of the previous lines and the words that are left to allocate, and yeah,
All
that's
right.
it.
Certainly he
The
needs to
current
know how many of the words has he read, because he needs to know which word to read next. He needs to know that. Does he really need to know the costs in the past? Right? We don't have to. He doesn't have to remember what mistakes have been done in the past. Is that going to help him? Knowing that there was one blank here, does that help him know what to do with the next word here?
No, but don't we need to like report that, like need to like report
Yeah,
the
good
law?
point. At the end, somebody will have to report, but that's not our problem.
Okay.
It's not Pooh Bear's problem. Pooh
Okay.
Bear is just, his problem is only, what do I need to know so I know not so I know what are the options in the future and what those options will cost me. He doesn't need to know how to make those decisions. He doesn't need to know how well he did in the past. Right? It's kind of like if you're gambling and you lose money, you gain money, right? You might say that influences what you do next, but the truth is, if it's a fair gambling, then all you need to know is how much money I knew now, and is the future going to be, what's the best future for me to do? Anyway, let's think about it. Do we need to know the number of words printed so far? Yes. Why? So we can know what word to print next, right? Do we need to know how they were printed or what they cost? No. Do we need to know how many lines they were printed on? Well, you might say we have to know which line we're on, but in some ways we don't care which line we're on, right? Do we need to, here's your question, do we need to remember the cost so far? No, right? What we do remember, we have to remember our current line. Is it completed, or how many spaces are left on it, right? When I get my next word, the next word is honest, I have to decide whether to put honest on this line or this line. And one thing I need to know for sure is how much space is there? Is there enough space to put it on that line, right? Everybody buy that? So we do need to know that, right? We need to know how effectively put the next word on the next line will affect, we need to know how it affect the current cost, right? Everybody kind of get that?
Yeah.
So, right, what states do we want to know? Well, we could do that algorithm that we just had, where right, so we could have an algorithm in which it remembers how many spaces are on the end of the line, all right? And that would work as a fine algorithm. But we're gonna do something indifferent. We're gonna have that at the top of the loop. I'm gonna assure you that whenever we're at the top of the loop, we're about to start a new line, right? So now, if all we're remembering is that what is the next word to remember to read, and we know that, suppose the fairy godmother here, she promises us that we're ready to start a new line, right? Then what do we need? These are the states that we might be in, right? Here's the state says, I'm ready to read the next word. The next word happens to be B. I'm ready to read it, and I'm going to put it on its own line. I mean, I'm not that it's going to be the first word of our next line. Everybody understand these states? So
Yes.
it might be that you never arrive at this state, right? It might not be a reasonable state to be putting. So I'm not claiming we're going to reach each of these states. We're only going to hit some of them. But these are possible states that we might get to. It's possible that we're ready for the fourth word, and the fourth word's going to go on a new line, right? These are possible states we might be in, right? Does that make sense? And you might be asking, well, why did I narrow it down to being we're at the beginning of a line? And maybe I should have done this algorithm over here where we're remembering the number of spaces, and we could have seen what the algorithm would have looked like. And it would have had a lot more states, right? For every, we would, you can see we have more states because we have the number of words here times the number of spaces on the line. So we would have had more states. Anyway, this has very few states. Everybody understand what these states are? Right? So it's not like all these states are going to be reached, right? So if the ith word never starts a new line, then we will never get in that state, right? But we don't know that we won't be in that state, but we might be in that state. So hence, we'll have that state in our graph just in case we need it, right? So, right, for example, in this solution, right, we're never in those states, right? Those states we don't get in. All right, and what's our S? S is we're at the beginning, we're ready to read the first word. T is we're at the end, we've read all the words, right? We have a table, right? Here, a table is going to be, we're going to store information about this state. Remember, we had when we're doing shortest path, we had a table which is had a sub problem for each state. How do we get the shortest path to that state? And now let's think about the actions that we might take. What we're going to ask the bird, right? So Pooh's going to have to locally decide what action to take, and so suppose he's standing on this state right here, right? He's standing here. He's ready to read the word B, and it might be pretty obvious that B has to go on some line. We're starting the first line. It's got to go in the first. Has to go in that first line. But what are the various actions that he could take? Remember, when he gets to a new action, new state, he has to fill that whole line in, right? So his action will be to fill in the line, right? He needs to fill in the next line with starting with here he's on the first word. So he needs to fill the next line, and it needs to start with the ith word. So what do you think we should ask the bird? What actions? What are the possible actions that he should take? If he wants to fill the whole line in, what does he need to know?
The number of words that we put on there.
Exactly, right? We ask the bird, how many words do I put in the next line, right? That's all he needs to know. He has to decide, how many words do I put on the next line, right? And the number of answers, well, he could put 1 word or 2 word or 3 word up to the number of words that actually fit on that line, right? So and he's going to have an edge out for every possible answer. So he might put one word on, he might put 2 words, 3 words, 4 words, right? Everybody see that these are the number, and if he puts 4 words on, then where does he move? He moves over to ready. I'm now ready to put the 5th word on a new line, right? Does that make sense?
Yeah.
All right. So what does the path look like? Well, the bird could tell him to put 3 words on. So here he did. He put the 3 words on. He moved over to B, right? He moves, right? There was a cost to doing that, right? The cost was there's one space on the end of the line, so you cube that, and so we're going to label this edge with cost of 1, and he's going to travel along there to this state, right? And then the bird tells him to put 2 words on the next line, so he does it. He's ready for the word. He moved past B and honest. What does this cost him? Right? This cost him 8. So he's going to label this edge by 8, and he's going to move along ready for the 6th word, right? And then the bird tells him to put 2 words on the last line, and so what does that one cost him? That cost him 27, and he moves over to, and he's done, right? Everybody see how he moved through the game of printing, and he followed some path. And we know that the total cost is 36, which is the length of this path, right? Everybody buy that?
Yeah.
Right. All right. So let's think about this optimal substructure idea, right? Remember, the weight of this edge, right? We said it was 8, right? It can't depend on what happened in the past or in the future, right? And do you see how it doesn't, right? If I'm ready for the 4th word, right? I'm ready for B, and B is going to go on a line B at the beginning, right? B is going to start this new line, and I decide to put 2 words, right? What will the 2 words be? Well, the 4th word is B, and then the 5th word is honest. So 2 words is be honest. So I know that be honest is going to be on a word by itself, a line by itself. Has nothing to do with what I did in the past. Has nothing to do what I'm going to do in the future. This action of putting be and honest on a line is going to cost me 8, no matter what. Everybody kind of follow that?
Yes.
Excellent. All right. So now let's think of all the actions, right? From B, right? I could put on 1 word in which I basically get this edge. And what is the cost of this edge? Well, it has 9 spaces. So this is a really expensive edge, right? And or I could put on 2 words, right? And it's less expensive, right? Or I could put on 3 words, right? And it has cost 1. Could I put on 4 words? No, they don't fit, right? So in some ways, taking this edge has a cost of infinity, or this edge doesn't exist at all, right? Does that make sense? Right? All right, and then we can go to, I'm ready for the 2nd word, right? I could say all the various possibilities, right? Where I'm starting with shore, right? I can say, I can put 1 word, shore, or I could put 2 words, right? 2 words, how many, what's it going to cost me? How many blanks are there? right? So I'm going to put in an edge for all of these options, right? Everybody see how this is an option. If I'm standing in the state where I'm ready for the word sure, and I put in the next two words, then the next two words would be sure to. And then if I put sure to in, then there's 4 spaces, and that's going to cost me 4 cubed, which is 64, right? So here I have this edge, which is costing me 64, right? Everybody buy that? It's a possible action in my game of life, right? Does that make sense? And I fill in all these possible states, right? Everybody get that?
Yeah.
So that gives us this whole graph. Each edge, right? We have our states, we have our edges, we know the weight of every edge, and right. So any solution that could be returned by the algorithm, here's the solution, corresponds to a path through this graph, right? And the sum of the action weights, right, is going to be the cost of this path of this solution, right? For every path through this, there's going to be a possible printing, a possible solution, and the sum of the edge weights along that path will be the cost of that solution, right? And so, and similarly, you take any path will correspond to a solution with the cost. So there's a one-to-one mapping between possible solutions with their cost and possible paths with their cost. Everybody buy that? And so we're going to be doing this reduction, right? We have an algorithm for solving the level graph problem. We're given an input to the printing neatly problem, right? And this input defines the graph, right? Because what do we need to know? We need to know the lengths of the words and how many words there are, and what is how many spaces are in each line. We need all that information to produce this graph, right? But this graph is easy to produce because it's all very locally, right? For each state, I say what edges are going to be coming out of this state, what actions do they correspond to, what will their costs be, right? I can produce this graph really easily. Now, how do I find the best way of printing? Well, the best way of printing corresponds to a path, the best path from S to T through this graph. And we don't have to worry about how to find this path. That's not our job, right? That's the job of our oracle. Our oracle will give us the best path, and that will give us the best way to print, and we're done, right? So all we have to do is, given our input, form our graph, and then take the solution, the best path through the graph that our oracle gave us, and form our solution. Everybody see that this alone is an algorithm that solves the problem, right? And what's the running time of this algorithm, right? We use Dijkstra's, we use dynamic programming to solve this problem. And the running time will be the number of edges, which, as I've sort of said, is also the number, it can be viewed as the number of states in the graph times the degree of each node, which also, in this case, the number of states in the graph is the number of words, and the degree of each node is the number of lines put on each, the number of words that can be put on each line, right? If I'm in this state, the number of edges coming out is, do I put 1 word, 2 word, 3 word? How many words fit on a line? That's how many edges I have coming out, right? Does that make sense? And I think I just had this slide because I was going to copy it if I needed it later, but I think I meant to delete it. Any questions about what we have? All right. So let's now just go back to the dynamic programming and think about how the dynamic programming would solve this problem. It's going to have a table, right? And for each line of the table, each entry of the table is going to be indexed by a number, and that number will be the name of the subinstance, right? The name of the state. And in this case, remember the state is how many words have I, well, and I guess, in the previous picture, this was what word do I look at next? And this is slightly different. This is how many words do I have remaining, right? I have to print 4, here are different words, right? I have 1, 2, 3, 4 words left. Right, so my subinstances, I guess my text is dumb. When I made this first example, I made it with various word lengths before I knew what the words were. And then I stuck in these weird words to make the right length. So it's a sillier sentence. But here my input are these words. And my 5th subinstance is how to print the first 5 words, right? The first 5 words are love life man while there. Anyway, it's a dumb sentence. My goal at this subinstance is how to print this sentence. And you might say, why are we doing it? Why is it the first 5 sentences and not the last 5 sentences? I think that's just an aesthetic thing. It's easier to think about what's the shortest path from S to a node than being focused on what's the shortest path from a node to T. So that's just an aesthetic thing, is that we want our subinstances all be paths from S to some node. So here, this is a path from S to the node where we've printed 5 words already, right? So the subinstances is how do we print these first 5 words, right? And what do we care about these words? We actually don't care that the word is love, right? So our characters are going to be the same width. So what we care about is how that there are 4 characters in love and 4 characters in life and 3 in man and 5 in while and 5 in there, right? So this is actually all we need to know, right? We have a line of, each line holds 11 characters. We have a word of length 4, 4, 3, 5, 5, right? That's everything we need to know to solve the subinstance. Everybody kind of get what this, how we're understanding this subinstance here? And then what is the solution to this problem? What is the optimal solution? Well, it turns out the optimal is to put 2 words on a line, 2 words on a line, and have 1 line with a single word, right? So we have 1 words on each line. You'll note that adds up to 5, which is the number of words we have, right? What was the bird? What do we ask the bird? We ask the bird, how many words do we put on the last line, right? What's the last, right? Remember, we asked the bird about the last edge. So here we're asking her how many put on the last line, and she tells us 1, right? And what's the cost of our solution? Well, don't worry about this right now, where the 16 comes from, but it turns out that the total cost is this 238, right? And we'll understand where those numbers came from in a minute. Everybody understand this line of the table?
Hey Jeff, not quite. Can you just re-explain it like in a better in another way so I can
Do
okay.
you understand? Do you understand what the sub instance is?
Yeah, the sub instances. I see it there. You have like the sub instances. Well,
Yeah,
yeah,
we got 5 words, and we know for each word how many letters there are,
each
right?
there's each word has like there are 4, 3, or 5.
4, 4, 3, 5, 5 is the number of letters in each word. You can see that's all we care about when we solve our problem, right? Because all the letters are assumed to have the same width. So all we care about is the number of letters, right? So that's our
So
subinstance. And given that, we have to say, what's the optimal solution? And it turns out that the optimal solution says, put 2 words on the first line, put 2 on the second, put 1 on the third, right? That's the solution,
okay,
right? And if you were to calculate the number of spaces and cube them, it would come up to this number.
okay,
Does that
okay.
make sense?
Yeah, so we have like the number of letters in each in each word, and then over there we have the sub solution.
Yeah, this is the solution, which tells us how many of these words to put in each line. We're going to have 3 lines with 2, 2, and 1 word on each line.
Okay, I see. That makes sense. Yeah.
Right. In fact, here's the solution: 2 words, 2 words, 1 word, right? And the bird's advice is put 1 word on the last line. Here, where do we get this cost from? Our cost from is 2 squared plus 2 cubed plus 2 cubed plus 6 cubed, right? That's how we got our cost, right? Does that make sense?
Yeah.
All right. So let's assume that we filled out this table up to here, right? We filled out the table, everything except for these entries here. And right, because by loop, right, our loop invariant is, what we're going to be doing is we're going to be solving this table, filling this table from the beginning to the end. And right, this first base case is clearly easy, right? We have no words, so you don't put any words on any line, and we have no cost, right? So the base case was certainly easy, right? The next case, we only have 1 word, so you put the 1 word on the line. That's straightforward, right? So let's say we've answered all of these questions, and we're now ready to answer this question right here, right? Does that make sense? All right, so now we're going to fill in this last line, and we're going to ask the bird, how many words do we put on the last line, right? Just like we asked, what's our last edge of our path? We're going to ask, how many words do we put on the last line? And she might say 1. And if she says 1, right, here, what is our text? Our text is all of the text, right? We have all 8 words. She tells us to put 1 word on the last line, so we trust her and we put 1 word on the last line, right? Then what do we now have to figure out? We know B is on the last line, so now we have to figure out how to print the 8 minus 7 words. So we ask our friend about the 7 words, right? And here we just look up in the table. Our friend tells us print 7 words by 223. So there it is. What is our solution? We trust the bird who said put 1 word on the last line. We trust our friend who said put 223 on the last on those lines, right? And that gives us our solution. It's a combination of our friend's advice and our bird's advice, right? Does that make sense? Right? And what will our costs be? Well, we don't have to calculate our entire cost because our friend already calculated the cost of these first 3 lines. our friend calculated the cost of this solution was 16, right? To get to this node, the friend followed a path from S to this node with cost 16, right? And then we have to take this last edge over to the decision of putting one word on the last line. And what's the cost of that last decision? Well, how many spaces are there? If you put one word on the last line, there are 9 spaces. So 9 cubed. So this is our total cost. This is the total cost of this solution. Everybody buy that? Any questions about how we did this line? Right? What is this? This is the best solution that we could hope for to our problem of printing all of this text, conditional on the fact that we trust the bird to put one word on the last line. Right?
Sorry, Professor, I have a question.
Yeah.
But if look at the 6 substance, if we add the, for example, we add the V and the B be the next 9, then the next 9 there's 2 words, the V and B, and the.
You're absolutely right, but you're getting ahead. Our bird told us to put one word on the last line, and we trusted the bird.
Oh, okay, thank you.
So, right? So you're absolutely right. Now the bird's going to tell us to put 2 words on the last line, right? So if she says put 2 words on the last line, then we know we're going to put 2 words on the last line, and as you said, those will be we be, right? So now if we put 2 words on, we have 8 words. Our bird put 2 words on the last line. That leaves us 6 words, right? 8 minus 2 is 6 words for our friend to tell us how to print those remaining 6 words, right? Friend tells us his solution is 222. So we trust the friend, and we put 222 is how we do the friend's part. And then we do the last line with 2 words, right? We trust the friend, we trust the bird, and that's how we get our solution, right? And how do we get our cost? Well, our friend said that the 222 solution has cost 43. So we trust our friend that cost, and then we want to say, what's our bird's cost? Well, our bird put 2 words on the last line, which leaves 6 spaces, and so 6 cubed gives us this solution right here, right? Everybody buy that? What is this? This is a solution to our problem of printing 8 words, subject to the fact that we trust our bird to put 2 words on the last line, right? Because we don't know how many words to put on the last line, right? So we're going to try them all. We'll try 1 word, we'll try 2 words, right? Now we're going to try 3 words. She says put 3 words on the last line, so we do that. 8 minus 3 is 5 words. We ask our friend how to print 5 words, and her friend says print it 221. So now we have 221 is our friend's answer plus our bird's answer. We combine those to get our answer. 2, 2, 1, 3, right, is our solution. What's the cost of our solution? Well, our friend says that the cost of 221 is 232, which is pretty high, but that's balanced out with our cost is only 3 cubed, right? So we get a total cost of 259, right? Everybody understand how we're doing this? Now we go to our 4th bird. Our 4th bird tells us to put 4 words on the last line, right? And what do we say to our bird? We say, bird, sorry, I can't put 4 words on my last line, right? So effectively, that one is not possible, right? That's kind of infinite cost to put 4 words on the last line. Everybody see how we've done this for all various bird answers?
Yeah, I got it. Thank you.
right? So what do we do now? Which answer? What's our answer?
Compare the
local best.
Right, exactly. We tried all bird answers, so we choose the best of the best. And you'll see these two solutions have equal cost. So we'll flip a coin and choose one of them to be our solution. It doesn't matter which. And what do? We fill in what our solution is. We fill in the bird's advice that worked for us, and we fill in what our cost is. Right? And then we're done. Everybody good with that?
Yeah, yeah.
All right. So if we wanted to write code for this, right, without, the dynamic programming code, without going through building a graph, then here's the code for it. And when we were doing it in class, the people in class couldn't read the font. And so I spent an entire day redoing slides to make these code fit so you could read it. 2:30, 3:34. We got another 11, 12 minutes, 10 minutes. How are people doing? I'm going to go through this code fast because we don't have much time. And if people don't understand it, we can do it again on Monday. Or no, on Wednesday. We still have a class on Wednesday. All right, any questions right now?
Yeah, I have a question.
Uh-huh.
So I think it's very helpful to visualize a DP problem as a DAG, like a
Right.
graph problem. But so is it but I mean, it's hard to solve a problem that way, right? Because to construct that like all possible like paths, like the cost to construct the graph might be is usually exponential.
No, but you're missing the point. You don't have to construct all the paths.
Yeah,
You
yeah.
construct all the edges.
Yes, the edges, but there's exponential number of edges, right?
No. Look at our graph here. Here's our graph. Right? How many edges are there? Well, how many nodes are there? There's a node for every word, right? You can't blame us for having a one node for every word. And then for every word, how many edges out? Well, it's how many words will fit on a line, right? So it's kind of 11, there are 11 words, spaces on each line divided by the number of words. So that's why I only have 3 possibilities out here, right? The number of edges here isn't very good, right? It's the number, it's the number of sub-instances times the number of bird answers per sub-instance.
Yeah, that's usually exponential, right?
No, well, sometimes it is, and then you don't have a good dynamic programming algorithm. But in this case, is it exponential?
So yeah, my point is, if we somehow can like pre-process the problem and convert it to a graph problem, then we can just run like graph algorithms like Dijkstra's or like other shortest path algorithms. But the cost or like the trade-off is that the pre-processing step might have like
how many edges do you think there's an exponential number of edges or polynomial number of edges? How many words can fit on a line? Is that a big number?
Yeah, I think for every word we can ask this question, do we start a new line with this word, right? So that's 2 to the n. That's 2 to the
No, but I'm just asking the number of edges. The number of paths is exponential. The number of edges is small.
Yeah, right. Okay, I got it now.
Right.
Like, is it always a polynomial?
No, for some problems, the number of subinstances or the number of edges become exponential. And then we don't have there are computational problems that don't have dynamic programming algorithms that are fast, in which case those, that's a problem. The number of subinstances here, I like to compare to how many people you invite to your wedding, right? So the bride and groom have to come to the wedding, right? Now, to solve their problems, they have to invite their friends, right? Because every subinstance has friends. So if you invite them, you invite the original instance, you invite their friends, and then you invite their friends, and then you invite their friends. Before you know it, everybody in the world is at your wedding. And if you've ever gotten married, you know that's the case. You can't invite Aunt Mary unless you invite her husband, right? Suddenly, even though you don't know her husband, right? So suddenly your wedding is blowing up. And in that case, we might have an exponential number of subinstances, and then our algorithm won't be very good.
Okay. So for every problem that we can run DP on, we can always convert it to a DAG, then we could run graph algorithms on it.
Yeah. Now, I never like it when anybody says the word every, because for every there's a counterexample. So at the end of these slides, we'll give a couple of graphs a couple problems that don't relate to graphs. And the reason is because we don't ask the bird one question, we ask the bird two questions. If you ask her two questions, then it becomes different.
Right. So so there's different types of dynamic program problems. So so for this particular one, we can run Dijkstra, I guess.
Yeah. Well, not Dijkstra. I mean, you could do Dijkstra's. I think it's better to do the dynamic programming, but because there's no cycles, right? Because there's no cycles, the problem's easier.
Yeah.
At one point in the slides, it said, or better use Dijkstra's, and I'm going to delete that because it's not better to use Dijkstra because we have no cycles.
Okay.
Anybody else have questions?
Professor, I just have a question about the test on Friday.
Yeah.
So it's gonna cover greedy, right? And then and then you're gonna give us more information as you make the test, because I saw your email saying something about the cases and.
2:30 on Friday, we will go over the test. And,
okay, so it's already made. Okay.
Yeah, well, I spent all day yesterday and most of this morning changing it. Is it in its final form? Probably not. The balance is, what do I give you as hints and what do I give as a question to make it so that everybody can get everybody can answer something, but nobody gets, here's the dilemma. If I give away early stuff in the test, then maybe that was the easy stuff and then people can't answer the hard stuff. On the other hand, if I don't give away the early stuff in the test and people don't get it, then they're crashed in the end of the test. So I give, it's hard for me to know what to give you and what to ask you. And just let you know that I do struggle with it.
Okay, no worries. Okay, thank you.
Any other questions? Next, so on Wednesday, I don't know whether it's going to be in class or I'm in communication with the health person at York as to what I should do. And you read different forms, they give you different answers. Ontario's guidelines are to only wait 5 days. So maybe 5 days means I can come on Wednesday. So I'll tell you Tuesday night whether we're in class or not. But you know, on Friday we're not in class because we'll be doing our tests. Any other questions? Excellent. So we will say goodbye then. Each node has 3 edges here. Yeah, a small number of edges. Okay.
I have a question.
Yeah.
Yeah. So it's a follow-up question. So we can like visualize it or conceptualize like a certain type of DP as a like graph problem, like
Yeah.
as a DAG, but we don't tackle that problem in the graph way, right? In the like we don't like the actual process where the setup like the code setup, like we don't like explicitly convert it to a graph. We don't pre-process the problem and convert it to a graph. Then do it in a graph way. We only visualize it that way, but we deal with the problem in a DP way.
Right. Yeah. Right. I would say you understand everything. I mean, you could pre-process it a graph and give it to your dynamic programming algorithm, the graph, or you could rewrite the code so that the graph is never actually stored. You work out the parts of the graph as you go along. When we certainly the code that we will look at, you'll see is completely mirrored with the code for solving it on the graph. The only difference is that the graph one will say, hey, what's this edge? And this one will say, hey, what edges did you have in mind? Right? So now you might ask, well, if I'm writing code that has nothing to do with graphs, why should I bother thinking about a graph? And different people think about problems in different ways, right? I know that when I'm thinking about a new dynamic programming algorithm, I have 2 completely different ways of thinking about it. The one way focuses on, I have my sub-instance, what am I going to ask the bird? I focus on the bird questions, the edges. And the other way I think about it is thinking, I'm going through the game of life. What sub-instances will I be? What states will I be in? And in some ways, having 2 different ways of visualizing it, you personally will decide maybe one works better for you or the other works better for you, or maybe when a particular computational problem arises, you'll try thinking about it as what do I ask the bird, and then you might try thinking about it as what sub-instances might I have. You can try thinking about it in these different ways, and having 2 different ways is, I think, will help you.
Yeah. So to code up that particular problem, it's like we build the graph along the way, right? Like we don't have the complete graph at the beginning before we process it. We build the graph like starting with the node, then we like construct the edges along the way, right?
Yeah. So the key line is I'm at a particular node, right? Here I'm at a particular node, which is I have a particular sub-instance in mind. I ask my friend for how to get a path to right. Then I ask my bird for a question, as in which edge should I take? And here I'm computing the weight of the edge, and here I'm combining my friend's subpath, sub-solution to this node plus the weight of the edge. It all boils down to the same, and we'll go through this code, and if people want to do some homework on this, you can go back to I redid the slides. Here, shortest path code. Remember, people couldn't read this code because the font was too small. So I just redid it so that at each point you see some of the code, right? And at some point, people should, should go over this and make sure they understand the parts of the code. All right, so here I'm explaining the different parts of the code. Everybody good with that?
Yeah.
And then we'll do the exact, this is for the graph code. And on Wednesday, we'll do the same for the shortest path code. And the two codes are absolutely mirrored. They're absolutely mirrored, right? The only difference is what are the subproblems, what are the edges? And we loop through the subproblems, and then for each subproblem, we loop through the edges going out of that subproblem, right? We loop through the BERT answers. It all boils down to the same thing.
Okay.
All righty, so we're running out of time, which is good because then we didn't have to get halfway into the code. Thank you, everybody, for all your great questions.
Me? Xianze.
Xianze.
Xianze, yeah.
Xianze.
Pretty close.
Thank you, Xianze, for your input. I really appreciate it a lot. And we will see you on Wednesday.
Okay, cool.